whoever wrote this paper, I don't know what you guys did to Cambridge because this paper is absolutely outrageous. I mean, the questions in here, it's borderline abuse at this point. Some of the questions, they're just not right for A level, for A level. But regardless, we'll get through the paper. But before we get into the paper, if you're writing CIE maths in October, November, and you're looking for more structured assistance, more personalized assistance than just going through past paper solutions on YouTube like this, I'm opening up a small live exam prep group where we'll go through P1, S1, P3, and S2, and we'll start roughly around mid-July. And the plan is that this will be a 10-week program where the first 6 weeks we'll do a crash course and cover the most important and most tested topics in that paper. And then in the last 4 weeks, it will be a past paper sprint. We'll work through full past papers together to make sure we can build up that exam strategy and make sure that you can confidently answer the questions by the time you get to the exam. And I want to keep the groups very small to ensure that I can actually give you personalized help to make sure you can improve. So if this sounds like something you'd need, click the first link in the description down below and fill in the short form. Tell me which papers you're going to be studying and when you're going to be writing these so I can see if you'd be a good fit for this group. And if you are, I'll send you the details so you can reserve your spot. Anyways, let's get into this outrageous February-March 2026 paper 32. Question number 1. Solve the equation 4 times 2 to the power of x plus 2 minus 5 times 2 to the power of 2 minus x is equal to 3. Okay. Not the worst start, but not the best start either. So what we want to do first is, I hope you can see using laws of indices there where I have a 2 to the power of x plus 2. According to laws of indices, this is just the same as 2 to the power of x times 2 to the power of 2, which is just the same as 2 to the power of 2 we know is 4. So it's 4 times 2 to the power of x, right? And we want to do something similar to this 2 to the power of 2 minus x. So we've got 2 to the power of 2 minus x. This becomes, again, according to laws of indices, this is 2 to the power of 2 divided by 2 to the power of x, because our powers are subtracting, right? Which is now just 4 over 2 to the x. So what this means is that here on the left hand side where we're saying 4 times 2 to the x plus 2, we've got 4 times 2 to the x plus 2 we've shown as just 4 times the 2 to the x. So 4 times 2 to the x, then minus 5 times, and then the 2 to the 2 minus x, this is our 4 over 2 to the x. And this is all equal to 3. Now just make things simpler and easier to follow, let's use a substitution. So we can say let t equal 2 to the x. So wherever there's a 2 to the x, we're going to replace with t. So I've got 4 times 4t minus 5 times 4 over t is equal to 3. Let's simplify. 4 times 4 is 16, so I've got 16t minus 5 times 4 is 20, 20 over t is equal to 3. And now I hope you can see where this is going. Get rid of the denominator, so multiplied through by t. So that's 16t squared minus 20 is equal to 3t. Move everything to one side, so I've got 16t squared minus 3t minus 20 is equal to 0. This is a quadratic. We are going to use the quadratic formula to solve this. So t is equal to minus b. So b is minus 3, so this becomes positive 3, plus or minus the square root of your b squared. So minus 3 squared minus 4a being 16 and c being negative 20. O divided by 2 times a, so 2 times 16. And then let's punch that into the calculator. This is 3 minus root 3 squared minus 4 times 16 times minus 20 over 2 times 16. Oh, what's an ugly number? They want their final answer to 3 significant figures. Okay. So I'll write this as negative 1.0282. Let's give them 5 decimal places for now. So just keep in mind that our final answer will be to 3 significant figures. So throughout our calculation, we always want to work with more than that. So t is either this or it could be 1.21571. And remember, we defined t as 2 to the power of x. So that means 2 to the power of x is equal to negative 1.02 821, or 2 to the x is equal to 1.21571. Okay. This first equation is not going to have any solutions. One way to think about it is this is an exponential graph, and if you know the shape of the exponential graph, you know that it is always above the x-axis. An exponential graph looks like this. And this is saying our exponential graph is negative, meaning it will be below that, which is not possible. So there are no solutions there. Another way to think about it is to be able to solve this equation, I have to take the logarithm on both sides. So I'd use log to the base 2 on both sides to bring down this x. And so I'd get x is equal to log to the base 2 of my negative 1.02821. And if you punch this into your calculator, you are going to get an error. So x is no solutions. And so as you can imagine, we're going to use the same idea of applying log to the base 2 on both sides. I'm using log to the base 2 because the base of my exponential here is 2. So if I want to get rid of this base, I have to use log with that base. Or you could just use any logarithm. So you could use, for example, ln to the power of 2x, and then you can bring down the power using laws of logarithms, x ln 2, and then divide both sides by ln 2. It's a bit more work, but that's another way of doing it. So apply log to the base 2 on both sides. You get x is equal to log to the base 2 of 1.21571. X is equal to, punch this into the calculator. So this is log to the base 2 of 1.21571, which gives us x is 0.282, correct to 3 significant figures. And that's our final answer. Question number 2. The complex number z satisfies the modulus of z is 9, and the argument of z is between half pi and pi. Part A. On the Argand diagram, sketch the locus of the points representing z. Okay. So the modulus of z is equal to 9. That's going to be a circle centered at the origin with a radius of 9. Because we know if we have modulus of z minus some complex number is equal to r, it's going to be a circle centered at a, b with radius r. In our case, this is just the same as saying z minus 0. So a would be 0 and b would be 0. So it's a circle centered at 0, 0 with radius 9. So we are going to draw that. So how good is my circle? I always mix these two things up. Let me think about it before I say it. Use your compass to draw your circle so that you've got a nice accurate circle. Okay, so this is a circle centered at the origin with radius 9, so it's gonna look something like that. Okay, and OneNote is not recognizing that I have drawn a circle. Nice. Okay, there we go. Let's just adjust this so that it looks like a circle of radius. Yeah, I think that's good enough. But again, use your compass to make sure you've got a nice accurate circle. So there's our circle. That's the first condition. The modulus of z is 9. Now the second condition is that the argument of z must be between pi over 2 and pi. So remember, argument is the angle formed with the positive real axis and your complex number. So I have to, from the origin, since this is just arg z, we are going to reference from the origin. So we're drawing with reference to this point. So from the origin, I have to open an angle of pi over 2. We don't need a protractor for this, but if the angle was different and less precise, so something in the middle, you'd need your protractor. But in this case, pi over 2 is going to be 90 degrees, which is pretty much this, right? And then arg z is less than or equal to pi, so that then becomes this. Let me straighten that up. So arg z being pi over 2 is this, and then arg z being pi would be the full 180 degrees. Okay. Now we need to find the points that satisfy both these restrictions. So the first restriction is that our z, we want a complex number z that's on the circumference, because that would mean the modulus of z is 9, and then we want a complex number whose argument is between pi over 2 and pi. So that means a complex number that's in the second quadrant and on the circumference of the circle. So what we're looking for is this. That's what we're looking for, and you can erase everything else. Here we don't shade because they didn't ask us for less than 9, which would mean inside the circle, or greater than 9, which would mean outside the circle. So that there would be your part A. Now part B goes on to say, on the same diagram, sketch the locus of points representing z star plus 3. Okay. So if I gave you a complex number z and it was 1 plus I, or just to stay in touch with their plane, if it was 3 plus 3i, if I gave you a complex number z that's 3 plus 3i, then that complex number would be there, right? 3 units in the real axis and 3 units in the imaginary axis. Now z star in that case would be 3 minus 3i. So that would be 3 units in the real axis. That's still the same. The only difference is that it's now minus 3 units in the imaginary axis. So what transformation is this to get from z to z star? It is simply a reflection in the real axis. Okay. So for us to first get from z to z star, I simply need to reflect this picture in the real axis. And so that's what we're going to do. If I reflect that in the real axis, then that's just going to be this. Bad reflection, but you get the picture. Use a compass. So this would now be z star. The green part would be z star. Now, what about the plus 3? So again, we can go back to our example. I don't know why I deleted that. We can go back to our example. We had z was 3 plus 3i. Now I want you to think about what happens if I add 3. If I add 3, let me not put it there. If I have z plus 3, this adds to the real part. We're saying 3 plus 3i, then plus this 3. All I'm doing is adding to the real part. So it now becomes 6 plus 3i. And that would shift my z, or translate my z 3 units in the real axis. So it would take me from 3, but now 6 at the same height. Okay. So this plus 3 is just a translation in the real axis by 3. So that means I have to shift to the right by 3. And so here we were intersecting at minus 9. When we translate by 3 to the right, we now intersect at minus 6. And our circle should now, or this bottom part, should now end at 3, because originally it was ending at 0. Okay. So that's going to be our z star plus 3, the green stuff. Let's delete this. I hope that makes sense. Question number 3. This is where the fun starts. Find the exact value of... In fact, before we even get into this question, there's something that I need to explain, because if you understand this idea of integration, it's going to be a recurring theme in this paper, and it's very crucial. It is the idea that the integral of f prime of x times f of x raised to the power of n with respect to x. So if you have some function of x raised to the power of n multiplied by its derivative, so the derivative of whatever is inside the bracket, then the integration of this is simply f of x. You add 1 to whatever n is, and you divide by the new power, plus c, of course. So for example, if I gave you the integral of, let's say, 2x times x squared plus 5 to the power of 6 with respect to x, I hope you can see that if I take whatever function I have in the bracket, x squared plus 5, and I differentiate that, if I differentiate this, I get 2x, which is what we have here. So I have f prime of x, and then I have f of x raised to the power of n. Our n is 6. So according to our rule above, this simply integrates to x squared plus 5. Then you add 1 to your power, 7, and you divide by 7 plus c. Another example. If I have, let's say I have sine x, and I have cosine of x, and let's say this is to the power of 5 with respect to x. So I hope you can appreciate that it's just the general standard to put the 5 there. But cos to the 5x simply means cosine of x all to the power of 5. So if I'm to differentiate my cosine of x, I know I get negative sign. Here I have positive sign. So to get to that f prime of x, I must put a negative sign there. But that now changes what the question is, so I need to correct that by cancelling out my negative sign. So now I have it such that I've got f of x and its derivative is negative sine x. So now I know I can just add 1 to this power and divide by the new power. So this would become cos x all to the power of 6 divided by 6, and because we added that negative sign, we had to cancel it. So negative plus c. I hope that makes sense. This is the idea we want to use in this question, and you see it later on in this paper, so make sure you understand. So question number 3, find the exact value of the integral from pi over 4 to pi over 3 of 3 sine x times sine 2x dx. Give your answer in the form p root 3 plus q root 2, where p and q are rational. Okay. So let's ignore the limits for now and let's just do the integration. So we want to do the integral of 3 sine x sine 2x dx. So obviously now, because I've primed you, you know we're going to be trying to get to this form, integral of f prime of x times f of x to the n. But don't rush it. Here we're not directly there yet, because if I try to, for example, differentiate sine 2x, that's not going to give me something similar to this. So what we want to do is, this is a double angle, and we know how to simplify double angles. So we know, according to the MF19, sine 2x is identical to 2 sine x cos x. So we'll use that. And so this becomes the integral of 3 sine x times 2 sine x cos x dx. Simplify that. We've got 3 times 2, which is 6. We'll just pull the 6 outside. And then we've got, I'll write the cos x first. We've got cos x multiplied by, I've got sine x times sine x, so sine squared x. As you can guess, I'm going to write it as sine x all squared with respect to x. Why? Because if I differentiate sine, I get cos. So this is my f of x, this is my f prime of x, and it's raised, my f of x is raised to the power of 2. So this simply becomes 6 times my sine of x, add 1 to the power, that's 3, divide by 3 plus c. So to answer the question, we have 6. In fact, this is 6 over 3. We can simplify that, right? It's just 2. So we've got 2, and then we've got our sine x all cubed, which is sine cubed x. And then we can bring in our limits, pi over 4 and pi over 3. So that's 2, and then substitute in your limits. And so this is the upper limit, sine of pi over 3, and this is being cubed, minus sine of pi over 4, and this is being cubed. Let's bring down that 2, it looks a bit high. So what is sine pi over 3? Make sure you're in radians. That's root 3 over 2. So this part that's inside, before we cube, that's just root 3 over 2. And this is all cubed, minus, and then sine pi over 4. This is root 2 over 2, and this is cubed. Okay, and now let's simplify. So I've got 2, and then here is going to become root 3 raised to the power of 3 divided by 2 cubed, which is 8, minus root 2 raised to the power of 3 divided by 2 cubed, which is 8. And we need to simplify root 3 cubed and root 2 cubed. I'd imagine most of your calculators can simplify root 3 cubed, if mine can. So you can use your calculator to do that. If your calculator can't, root 3 cubed is root 3 times root 3 times root 3. If I put brackets here, notice that root 3 times root 3 is just root 3 squared, which is 3. So this becomes 3 times our root 3. So 3 root 3. And similar idea for root 2 cubed. It becomes root 2 times root 2 times root 2. And if we put brackets there, this is root 2 squared, which is just 2, so 2 root 2. So what we have is I've got 2 times 3 root 3 over 8 minus 2 root 2 over 8. And multiply through by the 2. So that's going to be, don't know why I'm taking my calculator. That's going to be 3 over 4 root 3 minus, and then that's going to be 1 over 2 root 2. And that's the final answer. Question number 4. The coefficient of x cubed in the expansion of 1 minus ax to the power of 2 over 5 is 1. Part A, find the value of a. Okay. So we need to find the coefficient of x cubed. Right, we've got 1 minus ax to the 2 over 5. So this is binomial expansion. We need our binomial expansion formula, which is in the MF19. And it says 1 plus x to the n becomes 1 plus nx plus n minus 1 over 2 factorial x squared here plus n minus 1 n minus 2 over 2 factorial, not 2. It has to change because it was 2 factorial, they're 3 factorial, and they're multiplied by x cubed. So we are looking for the term in x cubed, meaning we are going to want this. That's the part that we want. So if you look at our expression here, our x is going to be this negative ax, and our n is going to be this 2 over 5. So I simply have to substitute in here with that in mind. So what we're saying is I've got n times n minus 1. So my n is 2 over 5. And then n minus 1 becomes 2 over 5 minus 1 times n minus 2. So 2 over 5 minus 2 divided by the 3 factorial times x. We said our x is this whole thing because what we're expanding has to be of the form 1 plus x. So this is 1 plus negative ax. So it's negative ax cubed. And we have to simplify that. So I'm going to punch this whole fraction into the calculator. That is 2 over 5 times 2 over 5 minus 1 times 2 over 5 minus 2 divided by 3 factorial. And that is 8 over 125. And then here I've got negative ax cubed. So cube the negative sign, it becomes negative. Cube the a, it becomes a cubed. And then cube the x, it becomes x cubed. So this is negative 8a cubed over 125 x cubed. So I hope you can see that our coefficient of x cubed is just this negative 8a cubed over 125. But we were told that this is equal to 1. So we just need to set that to 1. Let's shift this down. And so let's do that. So we're saying negative 8a cubed over 125 is 1. And now we solve. So negative 8a cubed is equal to 125. And so a cubed is equal to 125 over minus 8. Don't think that simplifies just yet. No. So negative 125 over 8. And then to get rid of the power 3, take the third root on both sides. And you should get a is equal to, so that 5, negative 5 over 2. Square root of negative 125 over 8. Oh, third root, not square root. Be careful with that. I was wondering why I'm getting an error. Gives us negative 5 over 2. Okay. And that's going to be the final answer. Part B says, hence find the coefficient of x to the power 4 in the expansion of 2x plus 1 times 1 minus ax to the 2 over 5. So I hope you can see this question feels a lot like the pure 1 question, except now just using the binomial expansion formula for pure 3. So 1 minus ax to the power of 2 over 5, that's the bracket we have in part A. So we already know the term in x cubed if I take this term in x cubed and I multiply it by the 2x, I'm going to get a term in x to the 4. However, if I also get the term in x to the 4 from this bracket multiplied by this one, I can also get a term in x to the 4. So I need to figure out what's the term in x to the 4 that I can get from this bracket. So if we were to finish off our binomial expansion formula here, it would then be n minus 1 times n minus 2 times n minus 3 as long over 4 factorial times x to the 4. So this is what we need to figure out. Okay. So that's going to be, our n is 2 over 5. So it's going to be n times n minus 1 times n minus 2 times n minus 3 all over 4 factorial times x to the power of 4, and we said our x is the negative ax to the power of 4. So let's put this whole thing into the calculator. That is 2 over 5 times 2 over 5 minus 1 times 2 over 5 minus 2 times 2 over 5 minus 3 over 4 factorial, which is negative 26 over 625 multiplied by, so be careful with how you simplify this. So raise the negative sign to the power of 4, it becomes positive. Raise the a to the power of 4, it becomes a to the 4. Raise the x to the power of 4, it becomes x to the 4. And so here we've got negative 26 over 625. We figured out what a was in part A, no pun intended. So substitute a in there. And let's simplify this. So I've got negative 26 over 625 multiplied by negative 5 over 2 to the power of 4, which is negative 13 over 8 x to the 4. Okay. And then we can also simplify this coefficient of x cubed in part A. So if we do that, we're just going to substitute a there. So it becomes negative 8 times negative 5 over 2 cubed divided by 125. That gives us, oh, that's silly. They did tell us that the coefficient of x cubed was 1. Okay, so we do know that this is just 1x cubed, right? So we've also got an x cubed here. So I've got x cubed minus the 13 over 8 x to the 4. That's representing the terms that we need from this bracket that are actually useful. And I want to multiply these terms by my 2x plus 1. So I want to get a term in x to the 4. So to do that, I need to take this 2x and multiply it by my x cubed. So 2x times our x cubed, or I can get x to the 4 by taking this 1 and multiplying it by this term. So that's plus 1 times negative 13 over 8 x to the 4. And so that simplifies to 2x to the 4 minus 13 over 8 x to the 4. And so if we simplify, that is 2 minus 13 over 8, which is 3 over 8 x to the 4. And so therefore the coefficient of x to the 4, coefficient, okay, there we go, of x to the 4 is 3 over 8. And that's going to be our final answer. Part C, state the set of values of x for which the expansion in 4b is valid. Okay. So if you go to the MF19, there's a condition for when this formula can be used. This formula can only be used if the modulus of x is less than 1. This is the same as saying if x is between negative 1 and positive 1. So they're saying whatever you have in the position of x, that thing has to be between negative 1 and 1. So in the position of x, we had negative ax. You can ignore the negative sign, it's not going to make a difference. So in the position of x, we had ax. So we need to make sure that the modulus of ax is less than 1. Or we need to make sure that ax is between negative 1 and 1. So that's what we need to do. So this expansion would be valid if mod ax is less than 1, which is the same as if ax is between negative 1 and 1. So let's make x the subject of the inequality, because they want the set of values of x. So that means x has to be between -1 over a. Wasn't a negative? Okay, now that's just silly. So we're gonna have to flip our signs quite a bit. So maybe let's substitute a first before we proceed, because we know the actual value of a. We know that a is -5 over 2. So this means this is -1 is less than -5 over 2x, which is less than 1. Okay. We can ignore this negative sign here, as in we can just completely remove it, because it's not going to make a difference. If I multiply through by -1, I'm going to have 1, and then my signs are going to flip because I've multiplied by negative, and then I'm going to have -1, which then just flips the whole thing back to, if we rewrite this properly, I'm saying 5 over 2x is greater than -1, which is less than 1, which is the same as me just completely ignoring this negative sign to begin with. So you can ignore that. And then multiply through by 2 over 5 to get rid of this 2 over 5 and make x the subject of our inequality. So you get -2 over 5 is less than x, which is less than 2 over 5. And these are the set of values of x for which the expansion is valid. Or you can write this as mod x is less than 2 over 5. Same thing. Question number 5. It is given that z is equal to 3 plus lambda I over lambda plus 2i, where lambda is a real constant. Part A, find the value of lambda for which arg z is equal to pi over 4. Okay, so we are given that z is 3 plus lambda I. The first thing that I want you to notice here is that I've got two complex numbers that are dividing each other. So this is division of complex numbers. And we know whenever we're dealing with division of complex numbers, I multiply both the numerator and the denominator by the complex conjugate of my denominator. So complex conjugate just means change the sign. Okay, so in our case, we are going to do that. This is 3 plus lambda I times the conjugate will be lambda minus 2i. And this is being divided by your lambda plus 2i times lambda minus 2i, which is, so I've got 3 times lambda, which is 3 lambda. Then I've got 3 times -2i, which is -6i. Then I've got lambda I times lambda, which is lambda squared I. Then I've got lambda I times -2i, which is -2 lambda I squared. And this is all being divided by, in the denominator, I've got a difference of 2 squares, a plus b, times a minus b. So that's going to be a squared minus b squared. So lambda squared minus my 2i all squared. And so let's simplify this. On the numerator, I've got, we know I squared is -1, so this becomes positive 2 lambda, and it's adding to 3 lambda, so that becomes 5 lambda. And then we've got, here we can group these terms, factor out the I, that forms our imaginary term. So if I factor out the I there, I then have lambda squared minus 6 times I. And this is all being divided by, this is lambda squared minus 2i squared, which is square the 2, square the I. So that part is going to be lambda squared minus 4i squared. We said I squared is -1, so that's lambda squared plus 4. So this is all being divided by lambda squared plus 4. Distribute the denominator, so I've got 5 lambda being divided by lambda squared plus 4 plus lambda squared minus 6 divided by lambda squared plus 4 multiplied by I. This is z. We now have z in Cartesian form, or the form x plus iy. And so because we have it in that form, we can now actually just calculate the argument in terms of lambda first, and then we compare that to the pi over 4. So if we are to, I feel like I've done this question recently for some very strange reason. If we are to calculate the argument of this, sketch it out. So we've got the real part of z, the imaginary part of z. Right, find the value of lambda for which arg z is pi over 4. So we've been told that arc z is pi over 4. So if I'm to draw out z, we need to draw out z such that arc z is pi over 4. Remember, the argument is the angle formed between the positive real axis and your complex number. So pi over 4 would be that angle over there. And this is z. So because this is z, this distance, this vertical distance, that's the imaginary part of z. That's whatever z, the imaginary part of z is, which is lambda squared minus 6 over lambda squared plus 4. So we're saying this vertical distance is lambda squared minus 6 over lambda squared plus 4. And then the horizontal distance, that's the real part. So 5 lambda over lambda squared plus 4. And this is a right angle triangle. So hopefully you can see that using SOHCAHTOA, I've got my opposite and my adjacent. So I can say that tan of my angle, which in this case is pi over 4, is equal to my opposite, which is lambda squared minus 6 divided by lambda squared plus 4, divided by my adjacent, which is 5 lambda over lambda squared plus 4. Okay, and tan pi over 4, we know that tan pi over 4 is 1. And this is equal to, because we're dividing there, I can change it to a multiplication sign and invert my fraction. So that's lambda squared minus 6 over lambda squared plus 4 multiplied by lambda squared plus 4 over 5 lambda. And hopefully you can see that these two will cancel out. And so what I have is 1 is equal to lambda squared minus 6 over 5 lambda. Multiply both sides by 5 lambda. 5 lambda is lambda squared minus 6. Move everything to one side. And we have lambda squared minus 5 lambda minus 6 is equal to 0. Looks like we should be able to factorize this. That's going to be factors of minus 6 that add up to minus 5. So that's going to be minus 6 plus 1. Okay. And so lambda is either negative 1 or lambda is 6. Are there any conditions that they gave us about lambda? They said lambda is a real constant. Okay. And let's see, we also have to think about the fact that from our diagram here, our real part here is going to have to be positive. If I substitute in lambda as negative 1, that's going to give us negative 5, because 5 times lambda, that's negative 5, divided by lambda squared plus 4, so negative 1 squared plus 4, which is 5, which is negative 1. I hope you can see that lambda is negative 1 would mean our real part is negative, meaning our real part is in the second quadrant, which is not what we have. Our argument would not be pi over 4. Okay, that will probably lead to an argument of whatever this is. I think that's 135 degrees or 3 over 4 pi, if my mental math is right. So we'd have to disregard the lambda is negative 1, because that would be pi over 4 except in the second quadrant. We want pi over 4 in the first quadrant. Okay, so we take lambda as to be 6. So therefore, lambda is 6. Part B. When lambda is the value found in A, find the exact value of the modulus of z, making your method clear. So what did we have z is? Z is this. Let's copy that. And we know that lambda is 6. So z becomes 5 times 6 divided by 6 squared plus 4 plus 6 squared minus 6 over 6 squared plus 4i. So z is equal to, that is 5 times 6 divided by 6 squared plus 4. That's 29. Ooh, I have to be very careful. I messed up my brackets. Don't be like me. This is 3 over 4. Okay, there we go. So 3 over 4 plus, and now the calculation for the imaginary part. So 6 squared minus 6 over 6 squared plus 4. That's, again, 3 over 4. How creative can you be? And we need to find the modulus of this. So the modulus of z, we know is just the square root of x squared plus y squared, if we're saying z is x plus iy. Right? And we have our z in that form, x plus iy. So our modulus of z is going to be the square root of 3 over 4 squared plus 3 over 4 squared. Do they ask for exact value? They did. Can our calculator do this for us? How far can it get? Let's see. If it does not give us an exact value, okay, let's just be good students and let's just show working. So we'll simplify what's under the square root first. So 2 times 3 over 4 all squared, 9 over 8. Okay, so this becomes the square root of 9 divided by the square root of 8. The square root of 9 is 3, and then the square root of 8 would be, if you punch that into your calculator, you should get, is it 2 root 2? Yeah, 2 root 2. And you can leave it there. If you want, you can manipulate it to bring the root 2 to the numerator, but they just ask for exact value, so you can stop here. Question number 6. The polynomial 2x to the power 4 plus ax cubed plus 4x squared plus bx minus 3 is denoted by p of x. It is given that x squared plus x plus 1 is a factor of p of x. Part A. Find the values of a and b. So initially, because you see factor, naturally you should be thinking factor theorem. But this quadratic, if you check its discriminant, it's not going to give you any solutions. Oh, yes, this quadratic when set to 0 would not give you any solutions. So this means we can't really factorize this nicely. So we can't use the factor theorem here. So what we're going to do is we will have to do polynomial division. And because we know this is a factor, if I divide this by a factor, the remainder I get when I divide has to be equal to 0. So that's what we're going to use to calculate our a and b. So I've got x squared plus x plus 1. And we want to divide 2x to the 4 plus ax cubed plus 4x squared plus bx minus 3. Don't be put off dividing by the a and the b. You just divide as normal. You just, of course, have to be extra careful because you're not dealing with normal numbers, yeah. So I use the term with the highest power in my divisor to carry out the division. So I'm going to say 2x to the 4 divided by my x squared. That's going to give me 2x squared. And then here I'm going to multiply 2x squared times my whole divisor. So 2x squared times the x squared gives me 2x to the 4. Then 2x squared times x gives me 2x cubed. 2x squared times 1 gives me 2x squared. And now I have to subtract this result from the above. So 2x to the 4 minus 2x to the 4 gives me 0. Ax cubed minus 2x cubed, that gives me, I'm just going to factor out the x cubed. That's a minus 2 x cubed. And then 4x squared minus 2x squared, that's 2x squared. Then bx minus 3. And we go again. So a minus 2x cubed divided by my x squared, that's going to give me a minus 2x. And now multiply this by the divisor. So a minus 2x times x squared, that's a minus 2x cubed. A minus 2x times x, that is a minus 2x squared. A minus 2x times 1, that's a minus 2x. And we subtract. So a minus 2x cubed cancels out with that. And then we have 2x squared minus a minus 2x squared. So let's just do that on the side. So I've got 2x squared minus a minus 2x squared. So this is 2x squared minus ax squared plus 2x squared. So I've got 2x squared plus 2x squared, which is 4x squared, minus our ax squared. And if you pull out the x squared, this is 4 minus ax squared. So we know there we've got 4 minus ax squared. Then here I've got, we'll do the same, bx minus a minus 2x. So bx minus a minus 2x. So that's bx minus ax plus 2x. And there's nothing that we can really simplify. So if we factor out the x, that's b minus a plus 2. So plus b minus a plus 2x. And we still have this minus 3. Okay, and we go again. So it's now 4 minus a x squared divided by our x squared, which just gives us 4 minus a. And so multiply the 4 minus a times the x squared. So that's going to be minus 4 minus ax squared, and then 4 minus a times x. So 4 minus ax, then 4 minus a times 1. So plus 4 minus a. Okay. Now simplify. So this 4 minus ax squared cancels out with 4 minus ax squared, that's 0. Then b minus a plus 2 minus 4 minus a. Okay. There's a lot going on there. So b minus a plus 2x minus, that's 4 minus ax. So if we expand everything, this is bx minus ax plus 2x minus 4x plus ax. So I hope you can see the ax's cancel out. And then I've got bx, and then 2x minus 4x. 2x minus 4x, that's minus 2x. So we've got b minus 2x. So that's b minus 2x. Okay. And then here I've got minus 3 minus 4 minus a. So that is minus 3 minus 4 minus a. Minus 4 minus a, that's just minus 3 minus 4, so minus 7. Then minus minus a plus a. So a minus 7 plus a minus 7. But remember, we said x squared plus x plus 1 is a factor. And here we've reached a point where we can't divide anymore, right? Because this x squared now has a higher power than what we're dividing. So this means this is actually the remainder. But we said this is a factor, so the remainder has to be 0, meaning that this term should have cancelled out this term to give us 0 here, and then this term should have cancelled out this term to give us 0, so that overall our remainder is 0. And so as a result, this minus this had to be 0, so that we have a 0 there, and then this minus this had to be 0, so that we have a 0 there. So that means b minus 2 has to be 0, and a minus 7 has to be 0, so that this remainder here is 0, because we're dividing by a factor. And so as such, we have that b is 2 and a is 7. And that's the final answer. Part B, hence show that x plus 3 is a factor of p of x. So this is the factor theorem. The factor theorem says if x plus 3, or rather let's write it this way. If a polynomial p of x is divided by a factor in this case x plus 3, or let's generalize it, x plus a, then we can say that p of negative a has to be equal to 0. This is the factor theorem. So if x plus a is a factor, then p of minus a is 0. So in our case, if x plus 3 is a factor, then p of minus 3 has to be 0. So we just need to evaluate p of minus 3 and check that it is indeed equal to 0. Okay. So p of minus 3. What's our polynomial p of x? Okay, it's that long thing. So let's just paste that there. And we now know that b is 2, a is 7. So p of x, maybe before we evaluate p of negative 3, we have that p of x is 2x to the 4 plus ax to the 3 plus, don't know why I'm writing a. We just said we know what a is. A is 7, so 7x cubed plus 4x squared plus 2x minus 3. Just substituting in a and b, right? And we need to evaluate p of negative 3 and make sure that it's 0. So this is 2 times negative 3 to the power of 4 plus 7 times negative 3 to the power of 3 plus 4 times negative 3 to the power of 2 plus 2 times negative 3 minus 3. Let's go term by term. So we've got 2 times negative 3 to the 4. That gives us 162. And then we've got 7 times negative 3 to the 3. That's minus 189. Then we've got 4 times negative 3 squared. That's 36. Then we've got 2 times minus 3, minus 6, minus 3. Okay. Let's add everything else here and just make sure that it gives us 189. So 162 plus 36. 162 plus 36 minus 6 minus 3. Yep. That's 189 minus 189, which is indeed 0. Okay. And we can conclude. Therefore, p minus 3 is equal to 0. So x plus 3 is a vector of p of x. And that's going to be our final answer. Question number 7, part A. By sketching a suitable pair of graphs, show that the equation ln x is equal to cosec half x has exactly one root in the interval x is between 0 and pi. Okay. We have to draw two graphs. So the two graphs we're going to have to draw are y is equal to ln x and y is equal to cosec 1 over 2x. I hope you know what the graph of the natural logarithm looks like. Before we get to the actual sketch, we'll just do the two graphs on the side. Okay, so the graph of the natural logarithm looks like this. That's your natural logarithm, and it keeps going up, but it's now decreasing. Or it's increasing at a decreasing rate, if that makes sense. And then it has a special point where it intersects the x-axis, and that's when x is equal to 1. All logarithmic graphs pass through this point, right? So this is y is equal to ln x. So that's not going to be a problem. Cosec, however, may be a bit tricky. So the way I like to think about drawing the graph of cosec is we know that cosec, or at least we should know that cosec is the same as 1 over sine. So if I know the sine graph, in theory, I should know the cosec graph. So my sine graph looks like this, goes up, then it goes down, then back up. So it peaks here at 1, minimum is at negative 1, and then this is 0. I believe we're in radians, right? Yes, we're in radians. So that would be pi over 2, and this would be 2 pi. Pi over 2 would be the peak. I have no clue why I've put pi over 2 there, but okay. And this is pi, and then that's 3 pi over 2. There we go. This is the graph of y is equal to sine x. If I have y equals sine x, I can draw the graph of y is equal to 1 over sine x, which is going to be cosec x. But here, what we want is the graph of y is equal to cosec a half x. So to reference this, I need the graph of sine of a half x. So sine of a half x, this is a graph that has been stretched in the x-axis by scale factor 2. Or, the way that I like to think about it, this half just tells us the number of complete cycles between 0 and 2 pi, or 0 and 360 degrees. So this is telling me that, this half is telling me that we only complete half of a full cycle between 0 and 2 pi radians. So this picture that I've drawn here, that's a full cycle. But we are saying for sine of a half x, I have to complete half of this cycle by the time I get to 2 pi. So that would mean I'm going to peak in the middle here. And so I want to complete half of the cycle. So this is half. If I was to complete it, of course, it would look like that. But we only want half of the cycle. So this red thing becomes the graph of y is sine of a half x. Okay. So we no longer need the blue stuff because we have the red stuff. So if I want cosec of a half x, that's 1 over sine of a half x. And we should know we're not allowed to divide by 0. So wherever sine of a half x is 0, I'm going to have a problem. I need to put an asymptote there. So that means I'm going to have an asymptote here because sine of half x is 0. And then I'm also going to have an asymptote at 2 pi. Okay. And then it's not really a reflection, but it looks like a reflection. And it approaches the asymptote, never actually touches that. This becomes the graph of y is equal to cosec of a half x. But I believe we only want it between 0 and pi. So that means we're only going to draw up to the middle, right? This part. Can put it in green. We're only going to draw that part. That's the one that's necessary for this question. Okay, so let's put this together. Let's draw our x's. This is my y, this is my x. We'll start with the logarithmic graph. It rises and then something like that. And here we're going to stop it at pi. Let me remove the arrow because we don't want it to keep going, right? We want to stop it at pi as per the domain. And then this we know would be 1. Okay, so let's make things make sense. Pi is 3.14, and if I'm saying that that's 1, that's a bit outrageous, isn't it? So let's maybe put pi somewhere there. Or rather, okay, I'm complicating things. Rather, let's just redraw this so that it actually looks like pi is somewhere there. So something like that, and this is 1. Okay, this is the graph of y is equal to the natural logarithm of x, and then we want to draw this graph here, the pink stuff, and we know it's gonna be this point here, this point there. It's gonna be 1. So when we get to pi, as you can see, when we get to pi, it has to come back down to 1. So it's gonna be, I'll draw it in red. This is y is equal to cosec of half x. And we are trying to prove that this equation has exactly one root, which means these two graphs have to intersect at exactly one point, which is this point. So circle it to show that that's going to be our root. And that's part A. Part B, verify by calculation that this root lies between 2.6 and 2.9. Okay, so we need our equation from part A. We have ln x is equal to cosec of a half x. Ln x is cosec of a half x. So what we need to do is to put both terms on one side, and then we're going to define this function f of x. So f of x is going to be, I want to move cosec to the left. So that's going to be ln x minus cosec of a half x. Okay. And this is going to be our f of x, and this is the function we use to verify if the root lies between 2.6 and 2.9. The big idea is, if we digress a little bit, if this is y, this is x, if I have some function f of x that looks like this is my y is equal to f of x. And let's say the equation I'm trying to solve is that f of x is equal to 0, i.e., what's this value of x when f of x is equal to 0? And using numerical solutions, the thinking is that if I pick a value here, so this is my x1, I hope you can see that this is going to have a positive y value, or f of x is going to be positive at this point. And if I pick a value after the root, so we'll call this our x2, f of x2 is going to have a negative. So if I try one x value, and then the next x value I try after that has a different sign, i.e. this one was positive, then this one had a negative sign, it must mean that my function has crossed the x-axis between x1 and x2. And so that's the idea we want to use. If we have a setup of f of x is equal to 0, and then I try two x values, and I find that between the two x values, I'm getting a change in sign of y values, it must mean we've crossed the x-axis between those two x values. And so my x value has to be between x1 and x2. So all we're doing here is looking for a change in sign. So let's evaluate f of 2.6. That's going to be ln 2.6 minus, You can't, or in some calculators you can input cosec, but if you can't, use 1 over sine. So this is 1 over sine half times 2.6. Make sure you're in radians. So this is ln 2.6 minus 1 over sine of 1 over 2 times 2.6. This gives us negative 0.0823. And then f of 2.9, this is ln 2.9 minus 1 over sine a half times 2.9. So that's ln 2.9 minus 1 over sine times a half times 2.9. This is positive 0.0574. So clearly there's a sign change. So it means our function must have crossed the y-axis between these 2 points, meaning our x has to be between x1 and x2. So let's make that conclusion. Therefore, since there is a change in sign, did they say the root or a root? Okay, this root lies between 2.6 and 2.9. And that's the final answer. Use the iterative formula xn plus 1 is equal to the exponential of cosec of a half xn to determine the root correct to 3 decimal places. Give the result of each iteration to 5 decimal places. Exponential of x is an alternative notation for e to the x, meaning they could have written that iterative formula as e to the power of cosec of a half xn. But as you can see, it doesn't look as nice because the power is pretty big. So that's why we're using this alternative notation. So that's what we're going to do. So we need an x0, a starting value. So you can use, you know that your root lies between 2.6 and 2.9. So you can use any value within this interval. We'll just use 2.6 as our starting value. So let x0 be 2.6. x1 is going to be the exponential of cosec. We said cosec is 1 over sine. So 1 over sine, and this is a half xn, so a half times x0, which is 2.6. And this is the exponential of 1 over sine of a half times 2.6, which is 2 point, they want each iteration to 5 decimal places. Okay, so that's 82306. All right. And now x2. So this is the exponential of 1 over sine. And then here we want to use the answer function on our calculator. So whatever you had as your x0, whatever you input for x0 in your calculator, replace that with ans, which is the answer function on your calculator. And then don't change anything else and simply press equals. So that gives us 2.75335. And now don't change anything on your calculator. Simply press equals. That gives us 2.77082. Again, simply press equals. This is 2.766. And this is 0.925 decimal places. We're looking for the answer to 3 decimal places. Oh wow. Okay. Again, simply press equals. This is 2.767. I think we've arrived. 3. And then this is 4. 1, 2, 3, 4, 5. Okay. If you round this off to 3 decimal places, oh no, we haven't arrived. We have to keep going because this is 2.766 and this is 2.767. Nice. So press equals again. x6. This is, okay, there we go. 2.767 and then 0, 1. This here is 2.767 to 3 decimal places. And this is 2.767 to 3 decimal places. So once you get 2 consecutive iterations with the same value, then you stop. That's your root. So therefore, the root is 2.767 That's the final answer. Question number 8. The variables x and y satisfy the differential equation y e to the 3x dy dx is equal to x times y plus 5. It is given that y is equal to 0 when x is equal to 0. Solve the differential equation to obtain an equation in x and y. Okay. So we have y e to the 3x times dy dx. And this is equal to x times y plus 5. This is a differential equation. So the first step is to separate our variables. So I need to move everything that is y to the left and everything that is x to the right. So that means this y plus 5 that's multiplying on the right will move to the left and divide. So I've got y over y plus 5. And then I'm going to keep my dy. And then this is equal to x. This e to the 3x that's multiplying on the left will move to the right and then divide. So e to the 3x. This dx that's dividing on the left will move to the right and then multiply. So dx. And once we've separated our variables, we want to integrate both sides. Okay. So on the left-hand side, we can't integrate this directly, but I want you to notice that this is an improper fraction. So the highest power in the denominator is equal to the highest power in the numerator, which means we have an improper fraction. And if you have an improper fraction, you first need to do the polynomial division, or you can do it in a slightly more efficient way, or more lazy way, if you will, which is what we're going to do here, because I'm not going to do polynomial division. I can't be asked. So what you do if you want to divide this without really dividing this is, so let's just go on a detour for a bit. Let's put it in red. You want to rewrite the numerator in terms of the denominator. Meaning, I'm just going to copy the denominator onto the numerator exactly as it is. Right, y plus 5. What do I have to do to my numerator to get back to the original numerator that I have? Well, there's an extra 5 that we didn't have originally, so I just have to subtract that 5. Right, because if I was to simplify this, that gives me back y over y plus 5. But I'll put a bracket here. This allows me to then distribute this denominator and have y plus 5 over y plus 5 divided by y plus 5 minus 5 divided by y plus 5. And this is equal to 1 minus 5 over y plus 5. And this we know how to integrate directly. So that means my left-hand side now becomes the integral of 1 minus 5 over y plus 5 with respect to y, and this is equal to the integral of this. Here I can just use laws of indices to bring the exponential up, and it becomes negative. So it becomes x e to the negative 3x dx. And I hope you can see that we are going to do by parts there. So on the left, if I integrate 1, I'm going to get, it's with respect to y, so I'm going to get y. And then I've got minus 5 ln y plus 5. If you want to be by the book, you'd have to put an absolute value here. But I'm almost certain that I'll forget to do this later on, so I'm just going to put no more brackets. And then if you differentiate the y, you get 1, so we don't really need to divide by anything. Plus a constant of integration, and this is equal to the integral of x e to the negative 3x dx. So let's do that on the side. So the integral of x e to the negative 3x dx, this is a product that we can usefully integrate by parts. And to pick what's u, use the late framework. So here L stands for your logarithms, A stands for your algebra, and then T is your trig, and then E is your exponentials. So whatever is higher up on the list, that's what you pick as u. So in our case, we've got algebra and exponentials. So algebra is higher up on the list, so I have to make u the x, and then dv dx becomes the exponential. So that's e to the negative 3x, and then differentiate u with respect to x, that gives us 1, Here I have dv dx, so I need to integrate to get v. So that's going to be e to the negative 3x divided by, differentiate negative 3x, that's negative 3. And now using the formula for integration by parts, it says the integral of x e to the negative 3x dx is equal to u times v, so that's x times this. So x e to the negative 3x over negative 3 minus the integral of v du, so this times 1. So e to the negative 3x over negative 3 dx. And hopefully you can see that our negative signs would cancel out there. So I'd end up having a plus, and I can get rid of this negative. And I'm dividing by 3, which is the same as multiplying by a third. So I can pull out 1/3. So I've got a third here. And hopefully you can see we've already integrated e to the negative 3x. That was our dv. If you integrate e to the negative 3x, it gives you that. So this is x e to the negative 3x over minus 3 plus our 1/3 times the e to the negative 3x over 3, rather over minus 3. And we can factor out e to the minus 3x over minus 3. And what remains is going to be x on the first term and then plus the 1/3. Okay. And that's the integral of x e to the negative 3x. And we substitute here. So that's y minus 5 ln, that 5 looks like an s. But we'll just, it's between you and me, you know that's a 5. Plus c, this is equal to e to the negative 3x over minus 3x plus a third. And we have been told that it is given that y is 0 when x is 0. So I can use that to evaluate c. So y is 0 and x is 0. So this becomes 0 minus 5 ln 0 plus 5. So 5 plus c is equal to e to the negative 3 times 0. So that's e to the negative 0, which is e to the 0. E to the 0 is 1. So 1 over minus 3. And then 0 plus a third. So that's just a third. So negative 5 ln 5. Oh, that really looks like an s. Negative 1 over 9. C is equal to, that's going to be 5 ln 5 minus 1 over 9. And now we substitute back here. So y minus 5 ln y plus 5 plus c, which is 5 ln 5 minus 1 over 9. And this is equal to e to the negative 3x over minus 3 times x plus a third. And I'm pretty sure they didn't specify to make anything subject of the formula. Obtain an equation in x and y. Okay. So this is an equation in terms of x and y, so we don't have to manipulate this or simplify this any further. So that's going to be our final answer. Question number 9. Let I equal the integral from 1 to 3 of x cubed over 3 plus x squared with respect to x. Part A. Using the substitution x is equal to root 3 tan u, show that I is equal to the integral from 1 over 6 pi to 1 over 3 pi of 3 tan cubed u du. Okay. This is where the fun starts. So we have I, which is the integral from 1 to 3 of x cubed divided by 3 plus x squared du, and we're also given the substitution x is root 3 tan u. So if we're doing integration by substitution and you don't know where you're going, do these two things first. First, substitute your limits and then differentiate your substitution. So let's start with the limits. So these limits are in terms of x, and we need to convert them to u. So at x is 1, I am saying 1 is equal to root 3 tan u, meaning that tan u is 1 over root 3. And so u is arctan of 1 over root 3. And so u is equal to, make sure you're in radians, 1 over root 3, that's pi over 6. And then we'll do the same at x is 3. So we're saying that x, which is 3, is equal to root 3 tan u. So this means tan u is equal to 3 over root 3. So u is equal to arctan of 3 over root 3. And so u is equal to, this is arctan of 3 over root 3. That's pi over 3. Okay. So these are going to be our new limits of integration. And as you can see, they match up with what we have there. Okay. So now we need to differentiate our substitution. So we've got x is root 3 tan u. So we're going to differentiate x with respect to u. So dx du. That's equal to root 3 times the derivative of tan. If you differentiate tan, you're going to get sec squared. So this is sec squared u. Okay. And so now we need to get du. So I need to make du the subject of the formula here. So we need du is equal to, that's going to be, simply swap these two, the du and the root 3 sec squared. So du is dx over root 3 sec squared u. Okay, so I've just realized that I made a mistake. Don't know if you noticed it. This is dx, so this should be dx, not du yet. So once we finish our differentiation here, what I'm actually looking to do is to get an expression for dx. So I need dx is equal to root 3 sec squared u times du. And now we can substitute. So we know we're now integrating. Instead of going from 1 to 3, we're now going from pi over 6 to pi over 3. So pi over 6 to pi over 3. And we are integrating. So x cubed, this is x. So wherever you see x, replace with root 3 tan u. So that's going to be x cubed, so root 3 tan u cubed. And this is being divided by 3 plus x squared. So that's going to be 3 plus x, that's root 3 tan u, and that's squared, times dx, right, times our dx, which we know is root 3 sec squared u du. So times root 3 sec squared u du. Okay, let's simplify. So this is the integral from pi over 6 to pi over 3 of, here, cube root 3. If you cube root 3, we did this earlier, this gives us 3 root 3, and then cube your tan, so tan cubed u divided by, that's 3, and then square the root 3, that gives you a 3, square the tan u, that's tan squared u, and this is being multiplied by root 3 sec squared u du. Okay, and now let's factor out a 3 in the denominator, because I can see it will cancel out with that 3, and it will also allow us to use an identity. So this is 3 root 3 tan cubed u divided by, factor out 3, so I'm left with 1 plus tan squared u multiplied by root 3 sec squared u du. So the 3's cancel out here. And then notice that we have an identity that tells us that 1 plus tan squared u is identical to sec squared u. Meaning that what I have here is the integral from pi over 6 to pi over 3 of root 3 tan cubed u divided by 1 plus tan squared u is the same as sec squared u. So sec squared u multiplied by root 3 sec squared u du. So this cancels with that. So we now have the integral from pi over 6 to pi over 3, and then that's root 3 times root 3, which is just 3 tan cubed u du. which is what we're trying to prove. And then part B, hence or otherwise find the exact value of I. Give the answer in the form P plus Q ln R, where P, Q, and R are rational. Now this question is borderline child abuse because, well, guess you see. Let me not spoil it. So we need to, we know of course I is equal to the integral from pi over 6 to pi over 3 of 3 tan cubed u du. We need to integrate this, right? And we can't do this directly. There's no obvious way for us to be able to integrate tan cubed directly. But what we can do is using the identity we've just talked about, this identity here. Right, we'll copy that down. We can say that I can write tan cubed u as, I'll just write this 3 outside the integral sign, so I've got a 3 here. And we can write tan cubed u as tan u multiplied by tan squared u du. Again, it's not a natural thing to do, but the idea is going to be we're trying to write tan squared u in terms of sec squared because we know how to integrate or deal with sec squared. That's the idea. It's not a natural thought, but this is the approach. So if you play around with the identity above and make tan squared the subject of the formula, you can see that tan squared u is the same as sec squared u minus 1. And so that means this becomes 3 times the integral. In fact, for now, let's just ignore the limits. We'll bring them back in at the end. So that's tan u multiplied by tan squared u, which is sec squared u minus 1 du. Okay. And this is what we need to integrate. For starters, we can just probably expand that. That's tan u sec squared u minus tan u. All of this is with respect to u. I think I'm going to write this as 2 separate integrals, which will make sense in a second. So the integral of 3 times the integral of the first part, tan u sec squared u minus 3 times the integral of tan u du. It may not be so obvious now, but we do know how to integrate both of these things. So the idea was to break down tan cubed u into something that we know how to simplify. We know once we bring in sec into the picture or sec squared into the picture, then it makes things much nicer because we know how to deal with that. Tan u, even though we don't have an immediate result for tan u, we do know how to integrate tan u, so that's also nice. And this is going to work with an idea we discussed earlier. If you've been watching up until this point, then you know exactly what I intend on doing here, or at least you should know. The idea is what we talked about earlier. If I have the integral of f prime of x times f of x, all of this to the power of n with respect to x, then this is f of x raised to the power of n plus 1 divided by n plus 1 plus, of course, your constant of integration. So hopefully you can see that here where I've got tan u, let me swap the order so that it's even clearer. So I've got sec squared u, and then I've got tan u. My tan u is raised to the power 1 because it's just tan, and this is with respect to u. And of course we've got the negative 3 tan u, but that's not the focus right now. So if you take tan u as your f of x and you differentiate tan u, we know that the derivative of tan u is sec squared u. So we already have this in the form f prime of x times f of x to the power of n. In this case, our n just happens to be 1. So that means this would integrate to f of x to the power of n plus 1 divided by n plus 1. So that means this simply becomes tan u squared divided by 2. Okay. So this becomes 3 tan squared u divided by 2 minus, we still need to deal with the integral of tan u. Okay, so if we focus on integrating tan u, so this you may or may not know from when you learned integration, but tan, we can rewrite tan as sine u over cos u. And for this, what we're trying to use is the integral of f prime of x over f of x with respect to x is equal to, so they should be a constant, k ln f of x, right? Which is to say, if you differentiate your denominator and you have the derivative on the numerator and some constant multiplying outside, then it's just k ln of the denominator. So in our case, if you differentiate cos, you get negative sign. So we're actually pretty close. If I put a negative sign, then I now have f prime of x over f of x, because the derivative of cos is negative sign. However, I introduced that negative sign, which was never there to begin with, so I need to cancel it outside the integral sign. And so now I can integrate this as k ln f of x, so negative ln cos u. Okay, so that means what we are dealing with is 3 tan squared du divided by 2 minus 3. Oh, because I've got a minus sign here and I've got this minus sign, it becomes positive. So plus 3 ln cos u. And we had limits, right? Pi over 6 and pi over 3. Okay, so we bring back our limits. Not the most straightforward of integrals. Pretty harsh from Cambridge if you ask me, but oh well. It is what it is. So now we substitute in the limits. So start with the upper limit. So 3 tan squared pi over 3 divided by 2 plus 3 ln cos of pi over 3. And then now the lower limit. So that's going to be 3 tan squared pi over 6 divided by 2 plus 3 ln cosine of pi over 6. Okay. Have I closed all my brackets? Yep. Okay. That's fine. Let's simplify step by step. So do tan pi over 3, and then whatever answer you get, square that. So tan pi over 3 is root 3, and then square that. That's 3. And so I've got 3 multiplying my 3 over 2, which gives me 9 over 2, plus 3 ln, then evaluate cos pi over 3. Cos pi over 3, that's 1 over 2, so 3 ln 1 over 2. This is the upper limit. Now let's do the lower limit. So again, do tan pi over 6. Whatever you get, square that. You get a third. So I've got 3 over 2 times a third, which gives me 1 over 2. Plus, then 3 ln cos of pi over 6. So we are going to do 3 ln and then evaluate cos of pi over 6. So cos of pi over 6, that's root 3 over 2. Okay. And now let's expand our brackets. So 9 over 2 plus 3 ln of 1 over 2 minus a half minus 3 ln root 3 over 2. Okay. Simplify like terms. 9 over 2 minus a half gives us 8 over 2, which is 4. And then I've got 3 ln half minus 3 ln root 3 over 2. Using laws of indices, I've got 2 logarithms that are subtracting, so I can combine them into one and then divide. So 3 ln, and I'm going to do a half divided by root 3 over 2. So a half divided by root 3 over 2. And so this is 4 plus 3 ln division, so I can change to multiplication and flip the fraction, which gives me 4 plus 3 ln 1 over root 3, which is root 3 over 3, but we can leave it like that unless they specified a more precise form. P plus Q ln R, and P, Q, and R are rational. Okay, so P, Q, and R are rational. So let's see. P is rational, Q is rational, this is not rational. Okay, so we have to do a bit of work there to get that rational. So remember, square root of something, that's an irrational number. So we can't leave it here. So what we're going to do is, using laws of indices, I can bring the root 3 up to the numerator. And that's just the same as 3 to the negative a half, right? If you've got 1 over the square root of 3, this is 1 over 3 to the half. And you can bring that up to the numerator as 3 to the minus half. And now what we want to do is I need to bring this power down so that what I have inside the bracket is rational. Because all I'm trying to get rid of is the square root sign, which is this power of a half. Once there's no square root, everything has become rational. So this is 4, and then I've got, if I bring the power down, I've got minus a half times 3 ln 3. And that's 4 minus 3 over 2 ln 3. Okay, this is rational, this is rational, this is rational. And that's exactly what they want, right? Yeah, okay. So that means I is equal to this, and that's the final answer. Real quick, before we continue with the paper, if you're writing your CIE maths in October, November, and you're looking for more personalized help, for more structured assistance, instead of just watching past paper solutions on YouTube, then I'm opening up a small live exam prep group for P1, S1, P3, and S2 that will start roughly around mid-July. And so this comes in 2 phases. First, we'll have a 6-week crash course where we'll cover the most important and most tested topics in your paper. And then we'll have a 4-week past paper sprint where we'll go through full past papers together to build out that exam technique and make sure that you can confidently answer past paper questions. And we'll keep the classes pretty small, so it's not just like a large, massive online batch. It will be between 5 to 15 students, so it will be very interactive, and I'll be able to assist you personally. So if this sounds like something that would help you out, click the first link in the description down below and fill in a short form. Tell me which papers you're writing, tell me when you're writing, and what you're actually struggling with. And if I think this group would be a good fit for you, then I'll send you the details and an option to reserve your seat early. Question number 10. The variables x and y satisfy the equation y squared is equal to k times x minus 2 over x plus 2, where k is a constant. Part A. Show that dy dx is equal to 2y over x squared minus 4. Okay. So I've got y squared is equal to k times x minus 2 over x plus 2. I should put k on the division line, but k is just multiplying our whole fraction. Okay, so on the right, because I have a fraction, I'm going to use the quotient rule. On the left, because I have y squared, I'm going to differentiate this implicitly. Okay, so this is technically implicit differentiation, where I differentiate the left-hand side separately and the right-hand side separately. Okay, it's just that on the right-hand side, I'm going to have to use the quotient rule to do my differentiation. All right, so if you differentiate y squared, you're going to get 2y dy dx. In fact, let's ignore that for now because we need to do the quotient rule. For the quotient rule, I need u and v. My u is going to be my x minus 2. And then my v is going to be my x plus 2. You can ignore the k for now. K is a constant, so it's going to multiply everything. So I'm going to differentiate this whole thing, and then I'll just have k multiplying everything. So I've got u and v. I need to differentiate. So du dx is going to be, if you differentiate x, you get 1, and then minus 2 is a constant. dv dx, you differentiate x, again you get 1, the 2 is a constant. Okay. So we said if you differentiate on the left, you're going to get 2y dy dx. And we said we're going to have the k multiplying everything. So I've got k times, and then the quotient rule says it's going to be v times du, which is x plus 2 minus u times dv. So minus x minus 2 in brackets divided by v squared, which is x plus 2 squared. And so we have that 2y dy dx is equal to k multiplied by here this x will get cancelled by minus x there, and then I have 2 minus minus 2, so 2 plus 2, which is 4, over x plus 2 squared. Okay, and if we make dy dx subject of the formula, I have dy dx is equal to, this is 4k over x plus 2 squared, and here you can think of this as me multiplying both sides by 1 over 2y to get rid of this 2y. So I'm going to have times 1 over 2y. So dy dx is equal to, I have 4 being divided by 2, so that's going to be 2, and we still have the k divided by, I've got my y times x plus 2 squared. Okay, so this is dy dx. What do they want? They want 2y over x squared minus 4. So what's the difference between what we have and what they have? We still have a k in our solution for dy dx, but we can tell that the final answer does not have a k in it. So that means we need to find a way to eliminate k. Our final answer is made up of x and y. So if we can find a way to rewrite k in terms of x and y, then we should be able to eliminate the k and eventually get to what they want. So do we have a relationship that links k to x and y? Yes, that's going to be the original equation, which is this. So we'd take that original equation and we'd make k the subject of the formula, which allows us to express it in terms of x and y. So that's going to be k has to be equal to y squared and then multiply by the reciprocal of this fraction, which just means flip the fraction over. So x plus 2 over x minus 2. This is k. And so let's copy that. So we know k is equal to this, meaning we can then rewrite dy dx as 2 times k. In fact, I'll write it like this: 2y times x plus 2 squared times k. Because k is multiplying in the numerator, I can also just pull the k outside and multiply like this, just so that it's not too messy. So I've got y squared times x plus 2 divided by x minus 2. Let's simplify. So dy dx is equal to, so I'm gonna have the 2 still, this 2 is still there. This y will get taken out by one of the y's here, and then I'm still gonna have 1y in the numerator, and then this x plus 2 will take out one of our x plus 2 here, and then I'm gonna have x plus 2 multiplied by x minus 2, and which is this x plus 2 and that x minus 2. And I hope you can see that this is a difference of 2 squares, a plus b times a minus b, which we know is a squared minus b squared. So in our case, we then end up with dy dx is equal to 2y divided by x squared minus 4, because a, which is x squared, minus b squared, our b is 2. And this is exactly what they requested. Dy dx is 2y over x squared minus 4. Part B, given that k is 5, find the angle between the tangents to the curve when x is equal to 3. Give your answer in the form a arctan b over c, where a, b, and c are integers. So this question tests a very niche concept that you probably have never seen before. You may have seen it before, but even then now the way that they test it here makes it a lot more difficult. But the idea at play here is that, let's illustrate this. If I have my x's, I've got y-axis, I've got an x-axis, and let's say we've got some curve. It can be any function really. Let's maybe drop it down a bit, and I want to draw a tangent. Right, so I've got a tangent to the curve at this point. Okay, so this is tangent to the curve. And the angle that this tangent forms with the positive x-axis, we'll call that angle theta. So we know that the gradient of the tangent to the curve is dy dx. But we also know that I can calculate the gradient of the tangent as being the change in y divided by the change in x. Right, so dy dx is change in y over change in x. Change in x. But notice that this is a right-angled triangle. So in fact, according to SOHCAHTOA, I've got the opposite as my change in y and the adjacent of this triangle as my change in x. So I can actually go as far as to say that TOA, where I've got opposite and adjacent, tan theta is going to be your opposite over your adjacent, which is simply your change in y over your change in x. Change in y over change in x. Meaning that change in y over change in x is simply equal to tan theta, where theta is the angle formed between your tangent and the positive x-axis. So this is equal to tan theta. So if we simplify this, we're saying that dy dx is equal to tan theta. Okay. Or you may see this in other forms as m, the gradient of your tangent, is equal to tan theta. So this is going to be the big idea at play here that we want to use. So I just move this to the side, but keep it in the back of your head. In fact, it will be the center focus of this thing, so don't forget it. Given that k is 5, find the angle between the tangents to the curve when x is 3. Give your answer in the form a arctan b over c, where a, b, and c are integers. So we need to find dy dx when x is equal to 3. Okay, because that would then give us access to theta, which is what we're interested in at the end of the day. Theta is the angle, right? So let's start by finding dy dx when x is 3. So because our dy dx is in terms of y and x, we first need to know what y is before we can get dy dx. So for that, we'd need to go to the original equation. They told us k is 5 and x is 3. What is y? So here we are saying that y squared is equal to k is 5 times x is 3, so 3 minus 2 over 3 plus 2. So y squared is equal to 5 times 3 minus 2 is 1 over 3 plus 2, which is 5. So y squared is 1, which means y is, take the square root, so plus or minus 1. So we've got two tangents. There's going to be a tangent, one tangent when x is 3 and y is minus 1, and then one tangent when x is 3 and y is positive 1. Okay. So visually, we're probably looking at, let's get the gradients first and then we'll visualize it. But we need to get dy dx for each of these tangents, right? So dy dx when x is 3 and y is minus 1. This is 2y over x squared minus 4. So 2y over x squared minus 4. So dy dx here is equal to, that's 2 times negative 1, that's minus 2. And then 3 squared, that's 9. 9 minus 4, that's 5. And I would label this as m1, because remember we say dy dx is gradient. So m1 is minus 2 over 5. And then we also have dy dx at 3, 1. So that's going to be 2y, so 2 times 1 over x squared, 3 squared minus 4. So dy dx is equal to, that's going to be 2 over 5. So m2 is equal to 2 over 5. All right, so let's visualize what's actually going on here. We can draw a rough sketch just so all of this makes sense. So we've got y-axis and x-axis and some weird looking curve. It's going to be weird because this is an implicit function. An implicit function is not actually a function because it fails the vertical line test, which is the definition of a function. But that's just a side note. That's not really like necessary for what we're doing. So I've got a tangent Let's adjust our tangent. This is it. X is 3, right? And y is 1. So the value there would be 1 and the value here is 3. Then I'm going to have another tangent down here, which is going to be, let's put that right there. Okay. So I've got another tangent here at -1. And so the first tangent here, that's got gradient. This one's got a positive gradient. So it's actually m2, positive 2 over 5. So m2 is equal to 2 over 5, and then m1 is our negative 2 over 5. So the question is asking us to find the angle between the tangents. So what we need to find is this angle here, that green angle. That's what we're interested in. So from earlier, we know that m, the gradient, is equal to tan theta, where theta represents the angle between the positive x-axis and the tangent. So if we zoom in on the red tangent, theta would be the angle that it forms with the positive x-axis. So that will be theta. And in fact, we can actually just call this A. So we are saying that we know that this one's the m2 one. We know that m2 is 2 over 5, and this is equal to tan of our angle between the positive x-axis and the tangent itself, right? So we know 2 over 5 is equal to tan A. And then, if we zoom in again, we know that m1 would then be equal to tan of this angle here, the angle that we form with the positive x-axis and our tangent. Okay, and we can call this our angle B. So we know that negative 2 over 5 is equal to tan of B. But what we actually want is this green thing, that's theta. Or we can define it as theta. So theta is therefore going to be the difference between the angles formed by the two tangents, which is going to be the difference between A and B. So theta is going to be A minus B, because if I can find what A is and then subtract it from B, it then gives me the difference between the two. And so traditionally what we would have done, the most obvious thing is to say, let me actually find the value of A, right? So you then say A is equal to arctan of 2 over 5, and you'd get a value for this. In fact, we can just temporarily do that just to see where the actual value. Of course, we're not going to want to go this route because they want it in a very specific form. Arctan of 2 over 5, I'm going to go in degrees just to illustrate this. This is 21.8. And then you would do B. So for B, we'd need to do arctan of negative 2 over 5. And so B would then be arctan of negative 2 over 5, which is negative 21.8. So we say theta is A minus B, so theta would then be 21.8 minus minus, so plus 21.8. So theta would then be, this is 21 plus 21, 42 plus 1.6, 43.6. So theta would be 43.6 degrees. That will be this green angle, which is the difference between A and B. Okay. However, notice that they say they want their theta in the form A arctan of B over C, which makes things a bit more complicated. So for us to do that, instead of going this way where we're just going to directly find A and then directly find B and get to theta that way, we can't do that. It's going to give us a decimal value, not an exact value. So what we can do instead is to look at this rule. We're saying theta is A minus B. We can take tan on both sides. So tan theta has to be tan of A minus B. And I hope you can see that this is a compound angle, right? Which means I can expand this using my compound angle formula from the MF19. The MF19 tells us that tan of A plus or minus B is equal to tan A plus minus tan B, all divided by 1 minus plus tan A tan B. Okay, and so we can simplify this using this formula here. So we can say that our tan theta is equal to tan A minus B becomes tan A. Follow the sign. Since we're taking tan A minus B, I have to take the signs on the bottom. So it's going to be tan A minus tan B, O divided by 1 plus tan A tan B. But we know the values of tan A and tan B. We know that tan A is 2 over 5, and we know that tan B is negative 2 over 5. So this becomes, we already know what tan A and tan B are. We know that tan A is 2 over 5 and tan B is minus 2 over 5. So tan A minus tan B becomes 2 over 5 minus minus 2 over 5. So that's 2 over 5 plus 2 over 5 divided by 1 plus tan A, which is 2 over 5, times negative 2 over 5, because that's what tan B was. And so this means tan theta is equal to, let's punch this into the calculator, 2 over 5 plus 2 over 5 divided by 1 plus 2 over 5 times negative 2 over 5, which is 20 over 21. And so theta is equal to arctan of 20 over 21, which would be the final answer, because this is the form that they requested for, right? And we can just double check that this actually gives us what we had. We had 43.6, and this does in fact give us the 43.6. So normally what I would have done is to just calculate A first and then calculate B. And then once I know the actual value of A, I know my theta is A minus B. But because they've specified that they want it in the form theta is equal to arctan of something, then we're forced to, if you have to backtrack, this is just the same as tan theta. If let's say I put an x there, this would be the same as saying tan theta is equal to x. So what we're being forced to do here is to say, instead of getting A and B first and then doing the subtraction, apply tan on both sides here first, and then simplify tan A minus B so you can get an expression for tan theta. Okay, it's a bit of a tricky question, not very straightforward and not ideal, but I hope that explanation makes sense. Final question. Question number 11. The points A and B have position vectors OA is equal to 2i plus 2j minus k, and OB is equal to 4i plus 2j plus 4k relative to the origin O. Part A. Show that the perpendicular distance from A to the line through O and B is a third root 65. Okay. Again, we need some sort of sketch to visualize this. So I've got, let's say this is O and this is B, right? This is a line going through O and B. And then I'm going to have a perpendicular distance from A. So I need a point A such that it forms a perpendicular line that goes to OB. So this is perpendicular. And I'll call the foot or the bottom of our perpendicular, I'll call that X. This is a sketch of what they want. A perpendicular from A, which is this line, and it's going through O and B. So it has to cut through O and B. Okay. And we need to prove that the distance of AX is equal to 1 over 3 root 65. Okay. So the key idea is that if you have perpendicular vectors, then the dot product of those vectors is equal to 0. So in our case, I know that AX is perpendicular to OB. So that then tells me that AX dot OB is going to be equal to 0. We know what OB is. We've been given in the question. AX, we don't know because we don't actually know the coordinates of X. But if you think about it, we've been told that this is a line going through O and B. And to get the equation of that line, we use the form R is equal to A plus TB, where A is a point on that line. I know that my origin is a point on that line because the line goes through O and B. So I can actually just use point A as my origin. So 0, 0, 0 plus T times, I need a direction for this line. This line is going through O and B. So my direction vector can be OB, which we know to be 4, 2, 4. So 424. Okay. So because it passes through the origin, I don't actually need to write this first part. So it just becomes r is equal to t times 424. And to get it in its component form, I can just multiply the t inside the vector. So it becomes 4t, 2t, and then 4t. This is the equation of our line going through O and B. Okay. We know that x lies on this line. And this equation gives me the general coordinates of any point that lies on this line. So this point B, its general coordinates would be satisfied by this. In fact, to get OB, I simply have to replace t with 1. And I hope you can see if I substitute t with 1, I get 424, which is exactly what OB is. It's 424. But for x, we don't know the actual coordinates of x. So we can get its general coordinates just by the fact that it lies on this line. So I can say that OX has coordinates of the form, or has a vector of the form 4, 2, 4t, 2t, 4t. Okay. And now this allows me to get a general form for AX. I know AX is going to be OX minus OA. And so this is our OX is 4t, 2t, 4t minus OA. We were given OA to be, I'll write it in column vector form. That's 2, 2, negative 1. So 2, 2, negative 1, which gives us that AX is equal to, if we subtract, this is 4t minus 2, 2t minus 2, 4t minus minus 1, so plus 1. Okay. And now we know AX and we know OB, so we can actually evaluate our dot product. And the idea here is I know AX in terms of t. If I can find the exact value of t, then that allows me to find the exact coordinates for AX. And once I know the exact coordinates for AX, I can then calculate the length of AX. And that's exactly what we're looking for. It's the length of the perpendicular. Right. So to find t, we then use this equation. AX dotted with OB is equal to 0. And so that means our AX, which is 4t minus 2, 2t minus 2, 4t plus 1. We're going to take the dot product of that with OB, which is 424. And this has to be equal to 0. Okay. So dot product, multiply the x coordinates. So 4t minus 2 times 4 plus multiply the y coordinates. 2t minus 2 times 2 plus multiply the z coordinates. 4t plus 1 times 4, and this is equal to 0. Let's expand. 4 times 4t, 16t, minus 2 times 4, minus 8. 2 times 2t, that's 4t, minus 2 times 2, that's minus 4. Then 4 times 4t, that's 16t. 4 times 1, that's 4, and this is equal to 0. Simplify like terms. 16 plus 4, that's 20, plus 16, that's 36t. And then minus 8 minus 4, that's minus 12, plus 4, that's minus 8. So minus 8 is equal to 0, so 36t is equal to 8, and then t is equal to 8 over 36, which is 2 over 9. Okay. So now that we know the actual value for t, we can find the exact vector AX. And once we know AX, we can then find its length. Okay. So let's just copy this. And so this becomes 4 times 2 over 9 minus 2. 2 times 2 over 9 minus 2. 4 times 2 over 9 plus 1. And let's punch that into the calculator. 4 times 2 over 9 minus 2. That's minus 10 over 9. And then 2 times 2 over 9 minus 2. That's minus 14 over 9. And then 4 times 2 over 9 plus 1. That's 17 over 9. So that's AX, and we need to find the magnitude of AX, or the distance. So that's going to be the square root of each component squared. So minus 10 over 9 squared plus negative 14 over 9 squared plus 17 over 9 squared. So let's punch that into the calculator. The square root of minus 10 over 9 squared plus minus 14 over 9 squared plus 17 over 9 squared, and that gives us root 65 over 3, which I'm pretty sure is what we were supposed to prove. A third root 65, yeah. Okay. And so that's going to be the final answer. Part B. The point C has position vector OC is equal to 3i plus pj plus qk, where p and q are constants, given that OC is perpendicular to AB. So once you hear perpendicular, you should be thinking about the same idea we used at the very beginning. If two vectors are perpendicular, their dot product is 0. And then angle AOC is equal to angle COB. Find the values of P and Q. Okay. So we've been told that OC dot AB is equal to 0. So this means that OC, if we write it in column vector notation, is 3PQ. This dotted with AB. We haven't found AB, have we? So let's find AB. Let me just copy OA and OB. Okay. So we need to find AB. AB is equal to OB minus OA, which is, if we write it in column vector notation, OB is 424 minus OA is 2, 2, negative 1. So that's 4 minus 2, which is 2. 2 minus 2, which is 0. 4 minus minus 1, so that's 5. So that's AB. So we can substitute our AB here is 2, 0, 5. And this dot product is equal to 0. So that tells us that 3 times 2, which is 6, plus P times 0, right, plus 5Q is equal to 0. So we've got 6 plus 5Q is 0. And so 5Q is negative 6. And so Q has to be negative 6 over 5. Okay, so we found one of them. Now we need P. So let's use the second bit of information. We've been told that angle AOC is equal to angle COB. Okay. So from the MF19, we get that cos theta is equal to A dot B over the magnitude of A times the magnitude of B. This is the equation we use when we're dealing with angle between two vectors. So we are dealing with angle AOC. Let's sketch that out. So AOC. So if I'm dealing with angle AOC, I need to pick the two vectors wisely. So I have an option here. I can either pick the vectors OA and OC as my A and my B. But what I can't do is to pick vector OA and CO. In other words, the two vectors that you pick should be going either both away from the angle or both towards the angle. So I could also do CO and AO, right? So the two green ones, or I could do OC and OA, but I can't mix green and red. That's not going to work. So in this case, the easiest approach for us would be to use OA and OC because we already know what OA and OC are. Okay. So that's going to be, let's call this is angle AOC. Let's call angle AOC, let's call it alpha. So we are saying that cos alpha is equal to, we said we'll use OA and OC, so the dot product of OA and OC divided by the magnitude of OA times the magnitude of OC. So we need to find the dot product of OA and OC. So OA we know is 2, 2 minus 1. So 2, 2 minus 1 dotted with OC. OC we know is 3PQ, but we found Q to be minus 6 over 5. So it's 3P minus 6 over 5. Okay. So that's going to be 2 times 3, which is 6, plus 2 times P, so 2P, plus minus 1 times minus 6 over 5, so plus 6 over 5. Which is, if we simplify like terms, we've got 6 plus 6 over 5. So 36 over 5 plus 2p. Okay. Now we need the magnitudes. So the magnitude of OA is going to be the square root of each component squared and then sum them up. So 2 squared plus 2 squared plus minus 1 squared. So that's the square root of 2 squared plus 2 squared plus 1 squared, which is 3. And then magnitude of OB, that's the square root of 3 squared plus p squared plus our negative 6 over 5 squared. Okay. So we know 3 squared is 9. And then we have the 6 over 5 squared. What does that give us? That's 36 over, what's 5 squared? 25. Plus 36 over 25 plus p squared. And we can simplify 9 plus 36 over 25. That gives us 261 over 25. So this becomes the square root of 261 over 25 plus p squared. So that means cos of alpha is equal to our dot product, which we found to be 36 over 5 plus 2p. 36 over 5 plus 2p divided by the product of the magnitudes. So magnitude of OA times magnitude of OB, which is 3 times this root. So 3 root 261 over 25 plus p squared. This is cos alpha, or cos of AOC. Right. Now we need to find angle COB. By the way, here you could then just do alpha is equal to arc cos, but you see why in a second. We don't really want to do that because it doesn't really help us much. Now we just need to do the same thing, but for angle COB. So with angle COB, we're looking at this. So this is C, this is O, this is B. Again, same principles. We need to pick vectors that are either going both towards or both away. So in this case, I'll pick OC and OB because we already know the values of OC and OB. And so if you call this angle beta, we are saying that cos beta is equal to OC dotted with OB divided by the magnitude of OC times the magnitude of OB. So we need to get the dot product first. So OC dot OB is equal to, so OC we know is, where's our OC? This is OC, our 3p negative 6 over 5. And then we also need our OB. OB is, where is OB? OB is 424, which is this one here. Okay. So that's dotted with, was it 424? Okay. We'll have to double check this one. Yep, 424. Okay. So let's simplify this. So it's 3 times 4, which is 12, plus p times 2, which is 2p, plus 4 times negative 6 over 5, which is negative 24 over 5. And this is equal to, let's simplify 12 minus 24 over 5. That gives us 36 over 5. And this is plus 2p. So that's the dot product. Now we need the magnitudes. We already found the magnitude of, OB. Why did we find the magnitude of OB? Or did I just label it? Okay, my bad. This is OC, the magnitude of OC. Because here we were dealing with magnitude of OA and magnitude of OC, right? And we did use these values to calculate, and that's OC. Okay, so that's on me. This is magnitude of OC. So we already know the magnitude of OC, and we need the magnitude of OB. So the magnitude of OB is going to be the square root of 4 squared plus 2 squared plus 4 squared. It's 2 squared plus 4 squared, which is, so square root 4 squared plus 2 squared plus 4 squared, that's 6. Okay, so cos beta is equal to the dot product, which is our 36 over 5 plus 2p, divided by our, what's our denominator? The magnitudes, the product of the magnitudes. I blanked for a second, which is 6 times the magnitude of OC, which is this, the square root of 261 over 25 plus p squared. Square root of 261 over 25 plus p squared. Okay, so this is cos beta. But remember, at the very beginning, they told us that angle AOC is equal to angle COB. So they said angle AOC is equal to angle COB. We labeled angle AOC as our alpha and then angle COB as beta. So in other words, what we are saying is that alpha is equal to beta. And we can apply cos on both sides, right? Cos alpha should therefore be equal to cos beta, which then means cos alpha is this expression. This has to be equal to cos beta, which is this expression. Okay. And so now we've got an equation for P, and we can solve for P. So probably the first thing that I would do, because it looks annoying, is notice that we have the same square root on both sides with the exact same values inside. So I'm just going to multiply both sides by that square root to get rid of it. So multiply both sides by root 261 over 25 plus p squared times root 261 over 25 plus p squared, which cancel out this. And so what we're left with is 36 over 5 plus 2p over 3 is equal to 36 over 5 plus 2p all divided by 6. Okay. And to get rid of the 6 and the 3, we can just multiply both sides by 6. Multiply by 6, multiply by 6. So on the left, I have 6 over 3, which is 2. So I now have 2 multiplying out 36 over 5 plus 2p, which is equal to, and then on this side, the 6 cancels the 6. So it's just 36 over 5 plus 2p. And so let's simplify. 2 times 36, that's 72 divided by 5 plus 2 times 2p, that's 4p, is equal to 36 over 5 plus 2p. And I'll put like terms on both sides. So I've got 4p minus 2p is equal to 36 over 5 minus 72 over 5. So that gives us 2p is equal to, that's minus 36 over 5. And then p has to be minus 36 over 5 divided by 2, which is minus 36 over 10. So p is equal to, what's that as a fraction? Looks like minus 3.6 as a decimal, but I want it as a fraction. Minus 18 over 5. Okay. So we can conclude that therefore p is negative 18 over 5. And q we said was, what did we say q was? Q was negative 6 over 5. And those would be negative 6 over 5. Those would be our two solutions for P and Q. Okay. And this will be the final question of this outrageous paper. So yeah, I hope you found this breakdown useful. And as a reminder, if you're writing your CIE maths exams in October, November, and you're looking for more personalized and more structured support, then I'm opening up a small live exam prep group where we'll cover Pure 1, Stats 1, Pure 3, and Stats 2 together. It will be me personally teaching you, and we'll have 2 phases to this program, where we'll first do a 6-week crash course where we'll go through the most important and most tested topics in that paper. And then finally, we'll have a 4-week past paper sprint where we'll solve full past papers together and make sure that you're exam ready and you build out that exam technique that you need to have. So if that sounds like something that could help you, click the first link in the description down below, fill out the form, tell me what you're struggling with, tell me what papers you're writing and when you're writing. And if I think the group would be a good fit for you, then I'll send you the details and you can reserve your slot. So see you on the inside.